Welcome to Dr. Raz, the Baking Chemist. Today's topic is Born Haber cycles. This is part of the Thermodynamics chapter, or if you're doing it Excel, it's Energetics Part 2. This is one of those questions where 1/3 of all students got 0 marks. At the end of this question, I will tell you exactly where students go wrong in all of these questions, and there are, as you will see, there are many places where students make mistakes or they go wrong. Okay, so right at the end of the video, I will highlight where things go wrong for the students. Okay, so make sure you wait till the end. Let's make sure we're not one of them. Let's do this. This question is about lattice enthalpies. The diagram shows a Born Haber cycle for the formation of magnesium oxide. Complete the diagram by writing the missing symbols on the appropriate energy levels. Okay, so obviously this is one of those classic questions where they give you partly filled Born Haber cycles. Now, before I actually do this question, I need 30 seconds of your time. For those people who are not sure what Born Haber cycles are, if you remember, you did Hess's law, and you should have done Hess's law before you get to this Born Haber cycle chapter or topic. Hess's law, where we're saying that if you start from the reagents or reactants and you get to the same product, it doesn't matter how you do it, the energy needed or the energy change is the same. And that's why Hess's law states that the energy change for a reaction is independent of the route taken. Well, Born Haber cycles is applying the Hess's law to ionic compounds. Now, if you imagine, this question is about magnesium oxide, so it's making magnesium oxide, and it's starting from magnesium and oxygen. Oops, so that's a solid, and that's a gas, and that's a solid. Now, if you imagine that this, when we start with magnesium solid, so in your mind's eye, visualize magnesium. It's a metal. Oxygen is a gas. When we react them, now you don't end up getting magnesium oxide by sheer magic. They don't just react and suddenly you end up with magnesium oxide. There are steps involved. There are stages involved. And those steps and stages involve energy. So Born Haber cycle shows you these stages and also the energy corresponding to them. Okay, now let's look at this for a second. Right, you start with magnesium. I'm going to tell you how Born Haber cycle works first before I address the question. Okay, so magnesium is a solid. You start with magnesium as a solid. Okay, now in order for the magnesium to bond with oxygen, and of course you need to know this is an ionic compound, you need to have magnesium, 2 positive charge, so magnesium ion, and also oxygen ion before they can ionically bond. So what happens is, obviously this is a solid, so what needs to happen is this needs to change in such a way that it ends up being a magnesium ion. And of course the same thing with oxygen. Oxygen is a gas at the moment. It's a diatomic gas. It needs to change in such a way that it becomes an ion, so then they're ready to bond together. Now, as a solid, these stages in Born Haber cycle, or in these reactions, in ionic compound reactions, these stages are always the same or similar. Okay, magnesium solid is first atomized. If you can imagine magnesium solid, it's like metallic bonding, all the positive centers with delocalized electrons around it. Well, they need to be separated into atoms. So the first thing that happens is magnesium is changed into atoms. Okay, once this has become atoms, it's still not ready. It's still an ion, so it's still not ready to react. So the first thing that happens is it actually needs to lose 2 electrons. So it loses 1 and then loses a second electron, and then of course it's ready. It's ready to react with the oxygen, as long as the oxygen is ready. And so what happens with oxygen is a molecule. So the first thing that happens is it gets atomized. So you separate the atoms. Okay, now obviously I've shown you a molecule consisting of 2 atoms, that's why I've written down 2, but actually magnesium oxide only needs 1 oxygen atom. So for the time being, and I'll explain it why, for the time being I'm only going to assume there's only 1 oxygen atom. But that oxygen atom is still not ready to react, because remember, oxygen needs to be an ion before it can react with the magnesium ion. So what happens here is oxygen accepts 2 electrons, accepts the first electron and then the second electron before it can become a negatively charged ion. And as soon as these 2 ions are ready, they will then ionically bond with each other to give you magnesium oxide. It's these stages that Born Haber cycle highlights and shows you, and of course the energy involved with each of these stages. Okay, so let's do this. So let's go on to the question now. So the question is, whenever you're doing, the question is to find out, so we need to complete this, okay? Born Haber cycles always start with elements, okay, and then a product, ionic product. So this is the elements in their standard states, solids and gases. So magnesium is a solid, oxygen is a gas, and you end up with magnesium oxide here. So all Born Haber cycles are like that, okay? So they start with elements and then you've got a product on this side slightly below, okay? And what happens is we've now got to show these stages that I was talking about onto the Born Haber cycle. And you can either show this stage first or this stage first, or sometimes this stage and then this stage and then this stage. So you can, but the point is the stages are the same. It's just how they're shown on the sort of Born Haber cycle might change. So keep that in mind. Okay. So let's look at what they're doing in the question. Magnesium solid is turning into gray magnesium. So that means nothing is happening in this stage for magnesium. But look what's happening to the oxygen. So what they've decided to do is they're atomizing oxygen. Okay, from O2 molecule to O. Now, the reason why they put a half here is because our end product needs an oxygen, only one oxygen. Can you see? This is why I said, oh, I only need one. Okay, and this is why they're putting a half here, because they know, and you should know, that magnesium oxide, there's only one oxygen, one magnesium. So that means you start with a half a molecule. Okay, and then of course that gives you the oxygen atom. And then from here to here, what have they done? Well, they've changed the solid to the gas here, so the magnesium. So obviously they're atomizing magnesium. They're not doing anything to that, but they still need to carry this along. Okay, you can't just not have oxygen here because, okay, well, this is the thing that's being affected, so therefore I'm not going to include that. No, you're going to lose marks. Okay, so carry this along. So nothing is happening to the oxygen, but magnesium is changing, or is being atomized. Okay, and can you see? I'll say that later. Okay, so the next thing now they want us to do is, well, what do you think happens here? Well, I'll come to the oxygen in a minute, but the first thing then that needs to happen is the magnesium needs to actually lose electrons. So what you end up here is you need to end up, and I hope people can see it, magnesium plus, so it loses, magnesium loses an electron, and of course you've got to put an electron there as well. Okay, you don't put an electron there, you're going to lose a mark. Okay, and of course I'm going to have to carry the oxygen along for the time being. Okay, so magnesium has lost an electron, but remember, magnesium is still not ready. Why? Because it needs to have 2 pluses. All right, so magnesium loses another electron here. So you end up with 2 electrons. Not 1 electron, because 1 is coming from there, so you can end up losing another electron, so there's actually 2 total electrons. Got to carry the oxygen along with me. Now at this point, magnesium is ready to react. Okay, it's got 2 plus, it's ready to make sort of an ionic bond with the oxygen. Oxygen is not. So now what oxygen does is it needs to accept these 2 electrons that magnesium has given it. Okay, or magnesium has given off. And therefore, oxygen has to accept an electron. But remember what I said to you? Oxygen accepting an electron, each electron is a separate step. Yeah, so oxygen will accept an electron, and I'll explain to you why it's going down in a second. Oxygen will accept an electron, but I've got to carry the magnesium along with it, remember? So I'm going to start with that. One of the electrons will be accepted, the other one will remain. And the oxygen that's accepted an electron, it will therefore become a minus. It's still a gas. Okay, and then of course, oxygen now, so that remember this is a gas, yeah? Now, oxygen will now then accept a second electron to become O2 minus. And at this point, these two ions are ready to make an ionic bond, okay, and therefore they'll make an ionic bond. Okay, now a couple of things. So for this part, it's worth 3 marks, and you know, the marks are obviously 1 for that, 1 for that, and 1 for that. But at this point, where people lose marks, and I will repeat this at the end, but where people lose marks, missing out electrons, missing out charges, and guess what I've missed out? And I would have lost a mark here. Look, that's missing out state symbols. Magnesium is a gas. Okay, missing out state symbols. Again, missing out, just leaving 1 electron there because thinking, oh well, there's already 1 there, isn't it? Yeah, might as well just put single one there, the new one that's been given off. No, you've got to put both electrons there. Again, state symbols. And here, again, charges. Sometimes they miss out, mistakes or whatever, they miss out charges. Okay, now this is where you got to be careful, that you got to carry all the things. So state symbols, electrons, charges, got to go on. All right. Okay. I said I'm going to explain to you why this arrow is going down and this arrow is going up. In Born Haber cycle, this y-axis is arbitrary energy axis. Okay, so if you go up on this axis, you get higher energy. In other words, it takes in energy. Okay, and if you go down, it gives out energy. So if you look here, elements, and here's the product. So going down, meaning this is sort of an exothermic reaction, it gives out energy. These processes take in energy. Yes, in other words, I've got to give its energy to break bonds. Okay, I've got to give it energy, I've got to put in energy to break the metallic bond to make into atoms. I've got to put in energy to remove an electron. I've got to put in another energy, or a lot more energy, to remove a second electron. Here though, oxygen, remember oxygen atom? It's only got 6 electrons in the outer shell, so it will accept 1 electron, yeah, and therefore become slightly more stable, so it will give out energy, yeah, because this oxygen needs 2 electrons, so when it takes first electron, yeah, it will give out energy, and that's why the arrow keeps going down. But the problem here is, well, oxygen needs a second electron as well. Why then does it take in energy? At this point, you've got to realize that this is a negatively charged ion. To this negatively charged ion, you're trying to add a negatively charged electron, and so therefore there'll be a repulsion process going on, yeah, and so you've got to overcome this repulsion to be able to make sure that oxygen accepts this second electron. And this overcoming of this repulsion is why you need to put in energy to make sure that oxygen accepts the second electron. Okay, and that's why second electron, you know, affinity, I'll explain definitions in a minute. Second electron affinity, etc., or third electron affinity are always endothermic. First electron affinity is exothermic. Second and third or subsequent ones are always endothermic. Okay. Anyway, so be careful about these mistakes. Let's move on to the next question. The table contains some thermodynamic data. Now, at this point, you really do need to know your definitions, okay? Because as you'll see in a minute, if you do not know your definitions, you may not be able to do this question, okay? So for example, enthalpy of formation of magnesium oxide. Well, if you don't know what the enthalpy of formation of magnesium oxide is, you may not be able to understand or identify which of these steps is enthalpy of formation. Common sense, you might be able to do it, yeah, but again, if you don't know the definition, you'll struggle, as later you'll see. Enthalpy of atomization. Okay, what I'm going to do is I'm going to label these steps. Just, you don't need to, but I am going to, because I'm going to explain it. Okay, so enthalpy of formation of magnesium oxide. So obviously enthalpy of formation is the enthalpy change for the formation of 1 mole of a compound from its elements under standard states. Okay, so this is enthalpy of formation. Enthalpy of atomization of magnesium. Yeah, so atomization is magnesium going solid to a gas, so that's the enthalpy of atomization, yeah, of magnesium. First ionization energy for magnesium, so obviously that must be this. So that just says 1 IE. And second ionization for magnesium, and that must be this. And that's the second ionization energy. And then bond dissociation enthalpy, I'll come back to that in a second. First electron affinity for oxygen. First electron affinity for oxygen. yeah, is that. So when oxygen accepts an electron, so that's the enthalpy and electron affinity, and maybe I should have put 1 EA, yeah. And then here, maybe I should put it down, otherwise I'm gonna have you're gonna complain about it. And a second electron affinity, so that's done. A second electron affinity is there. Second electron affinity. Okay. Now, the reason I said I'm going to come back to that is bond dissociation enthalpy for oxygen. You might think, hold on, the only one missing is that one, bond dissociation, and that one, of course. But what they want to do is calculate the value for the enthalpy of lattice formation, isn't it? So that must be the lattice formation, lattice enthalpy. Okay, and they want us to find that out. All right. Now, this one, the bond dissociation enthalpy for oxygen. Now, you might think, okay, well, that's bond dissociation. And look, bond is breaking, right? Dissociation. And this is where your definitions come in. Okay. What's happening here is the atomization of oxygen, enthalpy of atomization. The definition for the enthalpy of atomization is the enthalpy change when 1 mole of atoms are formed from the gaseous elements. Yeah. Now, we are therefore forming 1 mole of atoms, and therefore this is enthalpy of atomization. The definition for bond dissociation is the enthalpy change when 1 mole of bonds are broken. Now there's a very distinct difference here. Let's look at this oxygen that we're breaking bonds for. When I break one of these bonds, this one here, so one of these double bonds, what do I get? I get 2 oxygen atoms. The enthalpy change when you break 1 mole of bonds is bond dissociation. Now, when you break these 1 mole of bonds, I'm going to end up with 2 oxygen atoms. But I'm not getting 2 oxygen atoms. I'm getting 1 mole of oxygen atoms. So therefore, this here is not bond dissociation. This is atomization, because atomization means, the definition of atomization is when 1 mole of gaseous atoms are formed from their elements under standard states. So in other words, I need to form 1 mole of oxygen atoms, and therefore I need to start with half of that molecule. So if the bond dissociation gives me 2 moles of oxygen atoms, and I only need 1 mole because the atomization is atomization, therefore I need to half of that. I need half of that energy to give me energy associated with enthalpy of atomization. So in other words, this bond dissociation energy of oxygen is plus 496, so that means I need to halve it. In other words, half of enthalpy of bond dissociation. Yes, so whatever the enthalpy is given here, I have to halve it to make it enthalpy of atomization. And this is one of the other places where students go wrong. But anyway, so this is, you need to be careful of. Right, so how do you do this? I need to find that enthalpy of lattice, I need to find lattice enthalpy. So how do I do that? Here, you've got 2 ways of doing it. It depends on whether, you know, you're a sort of mathematical type person, or whether you're a visual person, you like to see things, okay? Let's talk about visual person, right? What you can do is you can say, well, okay, I need to find that. In other words, I need to go from here to here. Yeah? So in other words, I need to find that. However, there's a roadblock. I can't go here. I can't go from here to here. But remember what Hess's law says, yeah? It doesn't matter how I get from here to here, the enthalpy change will be the same. So all I do is, instead of going from here to here, which I can't, I can just go around here to get to there. And so if I go around here, the enthalpy change should be the same. So all I do is I literally add every single enthalpy to give me that enthalpy change. Yeah, so lattice enthalpy is equal to this plus this plus this plus this plus this plus this plus this. But being careful of one thing. If you do go across like that, every time you go against the arrow, so look at this, I'm going against the arrow. The sign, whatever the sign of that enthalpy change is, so this is the second electron affinity, isn't it? That's plus 844. I'm going against the arrow, so I've got to change that sign to a minus 844. Okay, I'm going against this arrow, so I've got to change the sign of that as well. I'm going against that, so I've got to change the sign. Against that, so I'm going to change the sign, change the sign, change the sign. Do not change the sign, yeah, because I'm going with the arrow. So literally I'm adding everything, remembering to change the sign whenever I'm going against the arrow. And that should give you lattice enthalpy. Okay. If you are a mathematical person, and this is what I'm going to show you by writing, I will use a formula. So the formula that I start with, and I'm going to have to change this. The formula that I start with is this. So I say enthalpy of formation of magnesium oxide is equal to, now this is what I always start with, enthalpy of formation is equal to everything else added together. So I'm literally going to say enthalpy of atomization, okay, enthalpy, but remember I've not been given enthalpy of atomization, I've been given enthalpy of bond dissociation, so I've got to put that down. So bond dissociation, however I've got to halve it, yeah, because remember I can't just say enthalpy of atomization because they've not given me enthalpy of atomization, so I've got to use what they've given me. Okay, so halve it, and that would be equal to the enthalpy of atomization, and then add that to enthalpy of atomization of magnesium. The next step is enthalpy of first ionization, enthalpy of first ionization, energy of magnesium, plus, I'm just going to come back here, enthalpy of second ionization of magnesium, plus enthalpy of first electron affinity of oxygen, plus enthalpy of second electron affinity of oxygen, and of course plus the enthalpy of lattice enthalpy. So there's your formula. Yes, it's a long formula, okay, but you got to put it down. You'll see why in a minute. And then remember what I'm trying to find out. I'm trying to find this out. So I've got to rearrange this formula to make that the subject of the formula. Okay. Now, what I can do is I can rearrange it now, but look, I don't want to have to spend another 10 minutes rewriting all of that. So what I'm going to do is I'm going to substitute the values for each of these. Okay. So delta HF magnesium is minus 602 equals, bond dissociation is 496, but I've got to halve it, 496, plus atomization of magnesium is 150, plus first ionization energy of magnesium is 736. Okay, so I've written that down. Now, to make my life easy, what I'm going to do is, rather than putting all these numbers on this side, because I remember I've got to make this the subject of the formula, so I've still got to move all of those across. But rather than moving all of those across as they are, I might as well just work this out and then transfer a single number. It'll be a simpler number, yeah? So I'm going to do that now. So minus 602, so equals 3286 plus your lattice enthalpy of magnesium oxide. Okay, and now what I need to do is move that across. Simpler, isn't it? 602, and this is a plus on this side, so if I want to move it across, it's 3286, 6 minus 3286, because that's a plus. Move it across, that becomes minus, and that will be the lattice enthalpy of magnesium oxide. And that, if I work it out, is minus 3888, yeah, kilojoules per mole. But they've given me already the units, and also they've not said in the question that they need units as well, yeah, with units. Okay, but I think, remember, you know, good chemists, yeah, you got to impress the examiner, so therefore I'm going to put the units in. But if you were doing that question, the units would already be there. Okay, and that would be your answer. Now, this is where people go wrong. Okay, mistakes. I've told you about the mistakes in the first part of the question. Second part of the question, where students make mistakes, is that's a common mistake. Okay, you know, they forget, yeah, that the bond dissociation is not the atomization energy. The second mistake they do is that they literally make silly mistakes, silly errors. Okay, so they start putting the wrong numbers, or, you know, for example, I've seen it where they said instead of 736 they put 763. Purely mistake. Yeah, it's because it's a rush, you know, exam situation, blah blah blah. Okay, so mistake, they lose a mark. Okay, because of that. The thing is, sometimes, remember, this is lattice enthalpy of formation of lattice, yeah? But if you go the other way, that's lattice dissociation, okay? So because the charge is here, they might have made a mistake, and they could have got a sort of a positive, so it's plus 3888, okay? That's a mistake as well, just be aware. Marks, yeah, you'd get a mark for that, a mark for that, and a mark for the answer. However, and this is why I always say show your working, right? Because if you had made that silly mistake there and you'd not shown your working, because as some students do, what they do is they literally take the calculator and punch in all the numbers, yeah, literally, rather than writing things down, they're punching all the numbers on the calculator and making that mistake, that 763 mistake, they end up with the wrong answer. And because they've not shown any working out here, they get 0 out of 3 marks. Okay, if you had shown the working out, you would definitely be able to get 1 mark for the actual formula. Okay, you would have lost a mark here, yeah, it's just that you would have lost this mark because you made a mistake here as well, but at least you would have got 1 mark. Okay, but if you'd not shown any working out, you would not have got any mark just because you made a mistake. If you hadn't done that and you'd just done that correctly, what you would have got is you would have got that mark, a mark for that and for that, and the same step. So as a minimum, I would have done that, and that would have given me both marks, 1 for that, because obviously I put in the values in the correct order. Okay, so I know what the formula is, so I can see what formula you're using here and what values you're entering, so I can give you both marks here. Okay, so you could have possibly missed out that and just gone for that, but remember, if you'd made a mistake, you would have lost marks. Okay, so in this kind of a question, look, this is a very number heavy question, a lot of number crunching, and students, because they're in a hurry, yeah, they tend to make a lot of silly mistakes. Okay, I hope that's helped you, and you know, if you have any other questions, any other suggestions that you want me to go over, please let me know, and I'll see you next Tuesday. Bye.